In this recording, we're going to have to look at errors in numerical computation. So there's two main types of error that occur in computational mathematics and computational techniques. These are round-off errors, which are due to computer hardware, and truncation errors, and these arise from the mathematics and from the algorithms that we're using. There are also errors known as overflow and underflow errors, and these are numbers that are too big or too small to be represented in a computer. And these are usually due to programming error, and they're not usually fundamental to numerical methods, and we'll have a look at those in a minute. Now, because these errors are introduced at every step of our computation, what happens to these errors as our computation proceeds is going to influence stability, and we will see later in the unit that stability is extremely important for all numerical methods. So let's have a look first of all at round-off errors. So in numerical computation, there are two basic types of numeric data. There are integers, also called fixed point numbers or whole numbers, and these are stored exactly. For example, 1, -43, 863, they're exact. There are also real, or sometimes known as floating point numbers. So for example, 0.0, 1.453 e to the -5, 43.333. All of these are examples of real and floating point numbers. In this unit, we are mostly going to work with real numbers, and these are stored and manipulated in scientific notation. And so what that means is the number, for example, 4132.561, will be stored as 4.132561 multiplied by 10 raised to the power 3. Now, of course, things will actually be stored as binary integers, but they'll use this same basic idea. So we're going to have a look at how a 32-bit floating point number is represented. It's equivalent in 64-bit architecture, however the numbers just get a lot bigger. There's a number of different representations of floating point numbers. I'm going to give you in particular the IEEE 754-2008 version, but others are equivalent to this, even though there might be some subtle differences. So our 32-bit number starts off here on the right-hand side with 0, and on the left-hand side bit 31, so it's numbered from 0 to 31. And the very first bit, or the last bit in actual fact, bit 31, is the sign bit. It tells us whether a real number is positive or negative. A 1 represents a negative number, and a 0 here represents a positive number. The next 8 bits, these ones here that are in green, are the exponent bits. And they are a signed integer that goes from -128 to +127, or sometimes it can be an unsigned integer which has an offset. So in other words, it goes from 0 to 255, but implicit in the definition is an offset of -127. This is a binary number that stores the value of the exponent, and it by itself is an 8-bit integer. Then the rest, which are the yellow points here, are 23 bits for the mantissa. Okay, and now this is a binary number of the form 1 point, then there's a series of digits. Okay, so implicit, so what we've actually got here in these digits here is the stuff after the decimal point. We're assuming that there's a 1 in front of it. Remember, this is going to be a binary number. So this 1 here is not stored because we don't need to store it. So these b's here are the multipliers of the powers of 1/2. So this one here is the multiplier of the power of 1/2. This second one here is the multiplier of 1/4. That third one, 1/8, etc. So let's just quickly go through and have a look at how to represent a couple of simple numbers in 32-bit representation. So the number 30.5 is equal to 16, and we've chosen 16 because it's a power of 2, multiplied by 1.90625. Okay, so 16 is 2 to the power 4, and 1.90625 is the digit. Now, this 1 point at the front here, 1 in decimal notation is the same as 1 in binary notation. So we've already got this as 1 point something or other. So what we now need to do is we need to worry about how can we represent 90625 as a binary mantissa. And it turns out, if you go through this, it's not that hard to do. It's 0.11101 base 2. Okay, and so this just means that this number is equal to 1 times 1/2 plus 1 times 1/4 plus 1 times 1/8 plus 0 times 1/16 plus 1 times 1/32. That's where this number comes from. And if you do this arithmetic, you will see that you'll get that's equal to 0.90625. So then this number is represented in our 32-bit notation as well. The sign bit is 0 because it's a positive number. The exponent is the binary number 100, which is equal to 4. And this thing here is the 0.90625, represented like this. Okay, so that's 30.5. Let's have a look at another number, 0.0068. If we go through the arithmetic, that's equal to 1 divided by 256 times 1.7408. And 1 divided by 256 is 2 to the minus 8. Again, we've got it in the form of 1 point something or other, so we lose this bit. And the 0.7408 in base 10 is this number here. And in base 2, this is a number that is has an infinite number of digits. It keeps on, well, I don't think there's any nice cycle there. It's what would be called an irrational number. It can't be written as a fraction in base 2. And so if we then plug this into our 32-bit floating point number representation, the sign of the number is positive, but the sign of the exponent is negative. So that's that negative, that's that 1 there. This is 8 in binary, and this then is the 0.7408. So we can see it looks pretty complex, but because we can add noughts and ones very simply, it means the computer can do it. So 32-bit real numbers have approximately 7 or maybe 8 significant decimal figures, depending on the number. They can be as small as 10 to the minus 40 and as large as 10 to the plus 40. Okay, so the first and main source of round-off error is caused by the finite number of bits in the mantissa. Now often we can't store all of these bits, and that's where we get round-off error. So for example, if you go into MATLAB and you were to type in my_pi is equal to this large number here with 20 or so digits, and then you asked MATLAB to print it out, MATLAB would stop at around about this point here, because these things here, which correspond to those things there, can't be represented in that floating point number. So that there is then the round-off error. Additionally, so it's not just the fact that you can't represent the numbers in the first place, but every time you do an arithmetic operation, for example an addition, a subtraction, exponentiation, functions, multiplication, anything at all, you're going to introduce more round-off error. And an important concept is this idea of a relative error, sometimes also called the machine accuracy, and that's equal to the actual error, in other words the magnitude of the error, divided by the magnitude of the number. So if you have a number 1 million and you do some arithmetic operation on it and the error is 10 to the minus 6, then the relative error is 10 to the minus 12, and it's small. If, however, your number is of order 10 to the minus 6 and the error is order of 10 to the minus 6, the relative error is of order 1 and the error is very significant. Typically, the machine accuracy, or the relative error, for a 32-bit computer is approximately 3 by 10 to the minus 8. Each time you do an arithmetic operation, you're going to introduce an error that has a magnitude, a size that's order this epsilon m here, this 3 by 10 to the minus 8, approximately. Now, it is possible that all of the errors could have the same sign, in which case if you do n operations, multiplications, additions, etc., the total error will be approximately n times the relative error. However, it turns out usually that the errors add up randomly. Some will have positive error, some will have negative error, and after n operations, more typically, the error scales like the square root of the number of operations. So you can see if you're doing hundreds of millions of additions and multiplications, which is something that you will do in this unit, you could see that the error could be quite significant. Some arithmetic operations are going to result in far bigger losses of accuracy. So for example, if you're going to add a small number, 10 to the minus 3, to a large number, 4 by 10 cubed, and let's do this in a hypothetical computer where we've only got a 4-digit mantissa. So we're going to play this a little bit loose. If we add these two numbers, the final result's actually what we started with. Well, sorry, it's equal to the large number if we only have 4 bits. And so we can see that by saying that our first number is equal to 0.4 times 10 to the power 4. Our small number is equal to 0.00, etc., 1 times 10 to the 4. If we add these two things together, we get this number here. But if we can only represent 4 bits after the decimal places, this bit here will go missing. And that's actually equal to this number here. So we've actually lost the effect of the small number completely. Another example, let's find the roots of the quadratic. I think we all know that formula there. Let's imagine that b squared is very much bigger than 4ac. So b squared is, say, 10 to the 10, and 4ac is just equal to 1. Now, if we're going to write this in scientific notation with the same exponent, then b squared is equal to 1 times e to the 10. 1 times 10 raised to the power 10. 4ac is equal to 0. There's a whole bunch of zeros there, I'm not too sure. And when we subtract these numbers here, remembering that we've got to keep these exponents the same, this thing here is so small that it won't even register against this big number here. So we do the subtraction, we actually end up with b squared. So the 4ac part is partially or probably totally disappears when we evaluate this. So then we're going to get round-off error. So truncation error arises from the algorithm we use, and in particular the mathematics that we've assumed. So in everything in computation, we're going to approximate a continuous problem using some kind of discrete method. And by discrete, we mean it only at a certain number of points. So for example, a really good example is the Taylor series. We've already seen the Taylor series in the last recording. It looks like this. If we used an infinite number of terms, it would be exact. If we use more terms, the approximation is better. But if we have to truncate it somewhere, so for example, let's say we're only going to use the first 3 terms, then we're going to say, well, y of x plus delta is approximately equal to this thing here. We know that there's some kind of error, and that bit there is the truncation error. The circle bit is the error that we know we're introducing. But we hope that delta cubed and the third derivative of the function aren't too big, so the error is small. Another example, let's look at the Taylor series expansion of the log of 1 plus x. I'm not going to go through this in detail, but you can easily show that log of 1 plus x is equal to this thing here. Let's just look at the expression where we take the terms up to the power of x to the 4th. That gives us this value here. If we actually look at the exact value, it's slightly different, 0.4054 versus 0.4010. And if we subtract these two things, the truncation error is the true result minus the approximate result, which gives us a value of 0.0044. This gives us approximately a 1% relative error. Okay, so this truncation error arises from the fact that we haven't considered x to the 5th, x to the 6th, etc., and the higher order terms. I've already mentioned that stability is an important issue. I'm not going to say much about it here. We will encounter this many times in this unit, but it's related to the interaction between our round-off and truncation errors and our numerical algorithm. So we've seen that round-off will always introduce error in a numerical method. You can't help it. As our method progresses, the error that we introduce at one step will either be reduced or magnified. We might introduce new errors as well, but we're interested in what happens to the old error. So if the error at one step is reduced at the next step, the method is usually stable. Not always, but usually. If the error is magnified, then the method is unstable, and eventually the error will swamp the solution and our approximation will become meaningless, and we'll see plenty of examples of this. And we're going to look at ways to determine the stability properties before we even do a computation. I've already mentioned underflow and overflow errors. These result from the fact that there's a maximum and minimum exponent that can be represented, approximately -40 and +40 for single precision 32-bit machines. So if real max, for example, is the largest number that we can represent in our computer, and then we multiply real max by 100, how are we going to represent that? The answer is we can't. And overflow and underflow are usually associated with other errors, either programming or instability. Something else you'll also get, and this is usually algorithmic in nature, is divide by zero. So it's 1 divided by 0, for example, and you'll get this thing that looks like NaN, which stands for not a number. And that's nearly always programming error. So, key points from this recording. Errors are important. You need to understand what the difference between round-off error and truncation error is, and know what overflow and underflow means. And we haven't done much on stability, but we'll see that stability is important in most things that we do. So the next recording, we're going to go through a brief MATLAB overview.